The great secret of the cosmos. White holes, the reverse of black holes? For time immemorial, humanity has gazed at the firmament, seeking answers to the universe's mysteries. Among the cosmic wonders, few entities have captured our imagination and challenged our understanding as much as black holes. These gravitational abysses, capable of devouring everything in their path, are the epitome of the unknown, the point of no return. But what if I told you the cosmic coin has two sides? What if for every black hole that mercilessly absorbs, there's a theoretical reverse that expels, spewing matter and energy into the universe? Prepare yourselves, because today we'll delve into one of the most fascinating and speculative concepts in astrophysics: white holes. Prepare your mind for a journey to the edge of physics, where rules twist and time might flow in ways you never imagined. Today, we're going to unravel the enigmatic hypothesis of white holes, those elusive inverse twins of black holes. Their existence is a debate that resonates in the minds of scientists, a question that forces us to reevaluate our conception of space, time, and, perhaps, the very origin of the universe. The origin of a bold idea, from Einstein's relativity to time reversal. To understand white holes, we must first dive into the ground where they were born: Albert Einstein's theory of general relativity. This masterpiece of physics revealed a revolutionary vision of space and time, where gravity isn't a force, but a curvature of the cosmic fabric caused by mass and energy. Within these equations, an astonishing mathematical solution emerged: the Schwarzschild solution, which perfectly describes black holes. Imagine a black hole as a cosmic drain, where gravity is so intense that not even light can escape once it crosses an invisible boundary called the event horizon. It's a one-way street, always inward, always towards collapse. But what if we play with time? What happens if we reverse the direction of time in those very same Schwarzschild equations? Eureka! By making this temporal inversion, suddenly, a new mathematical entity arises: the white hole. This idea, as bold as it is provocative, was thoroughly explored by Soviet physicist Igor Novikov in the 1960s. Thus, while black holes swallow everything, white holes, in contrast, would be entities that expel energy and matter, preventing anything from entering their interior. It's as if the universe took a breath, a point of massive exhalation instead of an inhalation. Portrait of a cosmic mystery: the fundamental characteristics of white holes. If we could glimpse a white hole, what would we see? Its characteristics, though theoretical, paint a fascinating picture. An inverse event horizon. Here's the key to its nature. Unlike a black hole, where the horizon is a boundary of no return inwards, in a white hole, the horizon would be an impenetrable barrier outwards. Nothing can enter, but everything can exit. Think of it as an inexhaustible source of light and matter spewing from the very heart of spacetime. Explosive energy expulsion. Imagine gigantic quantities of radiation and particles being vomited into space. White holes would be like cosmic lighthouses shining with unimaginable intensity, releasing colossal energy that could rival the most powerful explosions in the universe. A fleeting existence. Unfortunately for those wishing to see them, most quantum models suggest that white holes would not be stable, eternal entities. Rather, their existence could be transient, appearing and vanishing quickly, like a fleeting flash in the cosmic darkness. This, as you can imagine, greatly complicates their detection. Gravity persists. Although they expel matter and energy, don't be mistaken, white holes would still be massive objects. Their mass would generate gravitational fields that would profoundly affect the nearby environment, distorting spacetime around them, though in an inverted way to what we're used to with black holes. Weaving cosmic connections. White holes and other universe phenomena. The white hole hypothesis isn't an isolated idea. It surprisingly intertwines with some of the biggest mysteries of the cosmos. The Big Bang, a primordial white hole? This is perhaps one of the most mind-blowing connections. Some scientists have speculated that the Big Bang itself, the event that gave rise to everything we know, could have been the equivalent of a primordial white hole. Imagine all the matter and energy of the universe being released in a gigantic initial explosion, as if a cosmic white hole had exhaled all existence. Wormholes, bridges between realities? The equations of general relativity are strange and wonderful. Some solutions, like Kruskal-Zakari's coordinates, suggest that a black hole could be connected to a white hole by a spacetime tunnel, a cosmic shortcut known as a wormhole. Could these tunnels be a way to travel through space and time, connecting distant realities or even parallel universes? Gamma-ray bursts, the last breath of a white hole? Gamma-ray bursts are the most energetic events we know in the universe, incredibly intense flashes of light lasting only a few seconds. Some astrophysicists have speculated that these mysterious explosions could be associated with white hole-like events, releasing all their energy in a final, glorious burst. Beyond the classical, the implications of quantum physics. While general relativity gives us the theoretical framework, quantum physics steps in to add layers of complexity and possibilities to the story of white holes. In theories like loop quantum gravity, a revolutionary idea is proposed. Black holes might not completely disappear after evaporating through Hawking radiation. Instead of simply vanishing, they could transform into white holes, which, in turn, would release the information that originally fell into the black hole. Why is this so important? Because it offers a possible solution to the famous information loss problem, one of the biggest dilemmas in contemporary physics. According to quantum mechanics, information can never be destroyed. But if black holes devour it forever, where does it go? The idea of white holes recycling that information is an elegant way to reconcile these two pillars of physics. It's as if the universe has an undo mechanism for devoured information. The great challenge: how to detect the undetectable. Despite the fascinating nature of white holes, the sad reality is that to this day, there is no direct observational evidence of them. They are, for now, a purely theoretical concept. And there are good reasons for this lack of proof. Their existence would be ephemeral. As we mentioned, models suggest they would be short-lived. In a cosmos that operates on cosmic timescales, an event that appears and disappears in the blink of an eye is incredibly difficult to catch. Erratic and brief emissions. If they emitted radiation, they would do so briefly and erratically, which greatly complicates their identification with our current telescopes. It's like trying to capture lightning with a handheld camera. An unknown formation mechanism. Unlike black holes, which are born from the collapse of massive stars at the end of their lives, we don't have a proven mechanism for the natural formation of a white hole. How would they arise? Would they be the result of an exotic and unknown event? This is a crucial unanswered question. Reality or cosmic fantasy? The enigma of white holes. The existence of white holes remains a highly speculative hypothesis, with no empirical confirmation. However, they are not a mere invention of fantasy. They persist as a valid mathematical consequence of the equations of general relativity. This means that, within the framework of Einstein's physics, their existence is, at least, a theoretical possibility. If one day we manage to detect a phenomenon with the predicted characteristics, like an intense emission of energy that appears and disappears without an obvious visible source, or a cosmic explosion that defies all our current explanations, we might be facing the first evidence of one of these elusive objects. It would be a moment that would redefine our understanding of the cosmos. Conclusion: windows to a deeper universe. White holes, with their intriguing nature as the temporal reverse of black holes, represent one of the boldest extremes of scientific thought. Although their existence has not yet been proven, their study invites us to question the boundaries of our knowledge, the fundamental symmetry of time, and the profound connection between the most extreme phenomena in the cosmos. Exploring the white hole hypothesis isn't just about investigating an exotic and theoretical object. It's, in essence, seeking answers to the universe's greatest enigmas. It pushes us to reflect on the origin of the universe, the true nature of time. Is it a one-way street, or could it flow in both directions? And the ultimate fate of the information that seems to vanish into the abyss of black holes. They are a window to a universe even deeper and more mysterious than we imagine. A reminder that, even in the darkest shadows of space, there's always room for surprise and discovery. The cosmos has many more secrets to reveal, and perhaps, just perhaps, white holes are one of the greatest. And that concludes our journey through the mind of the cosmos. If this exploration has blown your mind as much as it has mine, don't forget to like this video, share it with your universe-loving friends, and, of course, subscribe to our channel to continue unraveling the greatest mysteries surrounding us together. Do you think white holes exist, and what role could they play in the universe? Let me know your opinion in the comments. See you in the next video.